complete what we started with, and then later should try to make some strategies, like if it is an online exam, no sorry, offline exam, so what should be your strategy, like how you should have what kind of approach. In today's class we'll be discussing about magnetic boundary condition. So this is a very important question, been asked in most of the previous year question papers. So what basically is this magnetic boundary condition concept? You might be asked a question to obtain, okay, obtain magnetic boundary conditions at interface between two magnetic materials. Let us have a boundary. Just assume this as a boundary which separates two magnetic mediums. I'll call this as mu1 with the magnetic permeability medium 1, and this region as mu2. So this is one region which belongs to mu1 magnetic material, and this is mu2 magnetic material, and you could see a white boundary separating these two regions. Am I audible, guys?
Yes, sir.
Hello?
Yes, sir.
Yes, sir.
Avan?
Yes, sir.
ಕೇಳಿಸ್ತಾ ಇದೆಯಾ?
ಸರ್ ಕೇಳಿಸ್ತಿದೆ.
Okay. So now I just wanted to know what is the magnetic field. What happens to magnetic field in single medium and at boundary between two materials? So here I am trying to observe what is the magnetic field here on the boundary. Okay, so I want to measure the magnetic field here, and I want to measure the magnetic field when entering from one material to another material. I just want to measure these two things. One, what happens with respect to the boundary. On the boundary, what happens to the magnetic field, and what happens if you're trying to enter, say, from mu2, and if you're trying to enter from mu2 to mu1, and what happens to this magnetic field. So I call this as normal component, and on the boundary I call it as tangential component, Bn and Bt. Similarly, I just writing the extended version here in terms of H. So this would be the component of Ht, that is tangential component, and this is a normal component. Now I am trying to measure Hn and Ht, or Bn and Bt. So what is normal component? Normal component exists while entering from one medium to another medium normally. It is perpendicular, and tangential over the surface of see here, this is over the surface, so this happens to be a tangential component of that boundary. So magnetic field is continuous in single medium, and at boundary between two materials it may change abruptly in magnitude and direction. So I would say H and B changes abruptly. abruptly where on the boundary, and we are trying to measure H normal component, H tangential component, B normal component, and B tangential component. So here you could see normal component and tangential component and of magnetic field and magnetic flux density will be measured. So I'm going to obtain the relationship between Hn, Bn and Hd, Bt. So how are we going to do this? So assume that B and H satisfy certain boundary conditions between two media of different permeabilities mu1 and mu2 as shown in this figure. So let us first try to determine the tangential component. So we shall take the first case 1, to determine tangential components. So in order to determine the tangential components, I'll be using Ampere circuital law. Okay. So in order to determine tangential components, I will use Ampere circuital law on the boundary. Similarly, for second case, in order to determine normal components, I will use Gauss law. Okay, so what is Ampere circuital law? I'll consider a rectangular path. Let me just draw it in a different color. I'll consider a rectangular path here. Okay, I'll consider a rectangular path. I'll call it as 1, 2, 3, and 4, and I'll make it in a clockwise direction. And this rectangular path is of width, say delta W, and height delta H. So this is delta W and this delta H. Is it okay? Is that okay?
Yes, sir.
Okay, fine. So now I'll consider a rectangular path. How is the path? Path is going from 1 to 2, 2 to 3, 3 to 4, and 4 to 1. So it's a closed loop. So you could easily see half is in each medium. So you have first half in medium 1 and you have second half in medium 2. Make a note of this figure because I'm going to go to the next slide. I'll move this board. Make a note of this figure because I'll come back to this figure again. I'll try to draw a Gaussian law, a cylindrical surface on the same figure in order to extract normal components. Now I am trying to extract tangential components by applying ACL. Next I have left out with Gauss law to find normal component. That I'll come back to this figure again. I'll draw a cylindrical Gaussian surface like this. To find a normal component. So here I will get the normal component and here I will get a tangential component. So how do you get tangential component? By making this delta H tends to 0. See here what happens if delta H tends to 0? Delta H tends to 0, what happens? If delta H tends to 0, are you going to be remaining with this 1 to 2 arrow and 3 to 4 arrow? Why? Because delta H is 0. So you're remaining with only these two lines, correct? Why? Because delta H is 0. So it will be exactly on the surface of this boundary. Correct? Yes or no?
Yes, sir.
Similarly, so I'll call this as N1 and here as N2. Similarly, I have a height of this cylinder, say delta H. If I make this delta H to 0, so I will be left out with these two arrows, that is N1 and N2, which is giving me the normal components on the surface. So this is with respect to a Gauss law. This is Ampere circuital law. Ampere circuital law to obtain tangential components, whereas Gauss law to obtain normal components. So now we are dealing with tangential components. If you are done with this figure, I'll go to the next slide. So now consider a rectangular path 1, 2, 3, 4, 1. So let the length, let the length 1 to 2 and 3 to 4 be known as delta W. Okay, and 2 to 3 and 1 to 4, 1 to 4 be known as delta H. Okay, so this is what I meant. So this is delta H and this is delta W. This is 1, 2, 3 and 4. And now as delta H approaches to 0, delta H approaches to 0. Ampere circuital law on the closed path can be given as, what is Ampere circuital path? So what is Ampere circuital law? HDL closed line integral HDL is equal to I enclosed. So this integral must be broken into 4 parts. Why? Because I have 4 paths here. So this will be an integral from 1 to 2 HDL plus 2 to 3 HDL plus 3 to 4 HDL plus 4 to 1 HDL, which is equal to total I. Okay, so entire integral parts can be broken into 4 different paths, which is equal to I. As you can see, delta H tends to 0. As delta H tends to 0, delta H tends to 0 means what? The paths associated with 1 to 4 and 2 to 3 is equal to 0, because there is no length at all here. So integrals from 4 to 1 and integrals from 3 to 2 tends to 0. So these two things, sorry, 2 to 3, right? This is 2 to 3. So this tends to 0 and this tends to 0 as delta h tends to 0. As delta h tends to 0, so this integral will become 0 and also this integral will become 0. So what is remaining there? Remaining is line integral 1 to 2 h dl plus 3 to 4 h dl, which is equal to I. So what is this h now? This h is a tangential component ht, and what is this dl? dl is equal to dw. Okay, dl is equal to dw. What is this? Again, h is equal to ht, but dl is equal to minus dw. Why minus dw? Again, I'll go back to this figure. See here, if I take the direction of 1 to 2, it is delta w, it is positive. And here, since I'm coming back, so this is of opposite of this direction, so I call this as minus delta w. So now I'll rewrite this integral equation. So I'll write it as 1 to 2. Shall I call it as ht delta w or dw? So delta w or dw minus 3 to 4 ht delta w, which is equal to I. Again, if you carefully observe this, 1 to 2 path is appearing and 3 to 4 path is appearing below the boundary line. That means this belongs to the medium 1 and this belongs to the medium 2. I'll go back to the original. See here, this path happens to be what? ht1, which is in the medium 1, and this path happens to be ht is in medium 2. See here, this is medium 1 and this is medium 2. So now I'll write it as ht1. This integral I'll write it as ht1, right? Because it represents the tangential component of magnetic field of medium 1 delta w minus ht2 delta w, which is equal to I. Okay, therefore I can write it as ht1 minus ht2 is equal to I by delta w, which is equal to k. What is this k? K is the surface current density. Surface current density. And obviously at a boundary. So it is constant. So what happens if the surface current density is 0? If K is equal to 0, that means if you have a surface current on the boundary as 0, then I can write it as HT1 is equal to HT2. This is how the tangential components are related with respect to the boundary separated by two mediums. So similarly, what is the tangential component for B? So what is B is equal to? B is equal to mu H. Therefore, I can write it as BT1 by mu T1 is equal to BT2 by mu T2. So this is the tangential component of magnetic flux density. So what is the observation here? Tangential components of H is same, correct? H is same on the boundary, whereas here, see here, mu T1 and mu T2. Mu1 and mu2 are different values. That means these two are in different mediums. Therefore, BT1 is not equal to BT2. That means it is discontinuous. H is continuous. HT component is, this is what you need to conclude. HT is continuous, but BT is discontinuous. On boundary with zero current density. Any doubt?
No, sir.
So I'll go to the second case now. What is the second case? I want to draw, or I want to determine normal components now. So how to determine normal components? As I said earlier, I'm going to apply or rely on Gauss law. To put up that boundary conditions figure here, mu1 and mu2 separated by a boundary, and apply Gauss law. So this is a cylindrical Gaussian surface, I'll imagine. So this is what a normal current Bn1, and this is a normal C with respect to N2, and this delta H tends to 0 in order to find normal components now. And then I'll see what happens with respect to Hn and Bn in terms of Hn1, Bn1, Hn Gauss law for magnetic field. So what is Gauss law for magnetic field? Surface integral ds equal to 0. Gauss law for magnetic field. So now the surface integral, how many surfaces I have? 3 surfaces. This is one top surface, bottom surface, and I have side surface. So the surface integrals will be split into 3 integrals: top, plus bottom, plus side, which is equal to 0. Again, I will be applying the same concept here. I'll make the length of the cylinder approach to 0. That means delta H tends to 0. I repeat, in order to find the normal components, I'll make this delta H tends to 0. Let me just write this BDS components also. So what happens if delta H tends to 0? This will be 0. So this will be 0. If delta H tends to 0, therefore the side integral will become 0. So the remaining is the top side and the bottom side. So I'll write the top side as Bn1 dot ds minus, why this is minus? Because it is at the bottom side, Bn2 into ds, which is equal to 0. Why negative sign? Why? Because it says surface at bottom. Therefore, I can write Bn1 equal to Bn2. So what is the conclusion now? The conclusion is the normal component of magnetic flux densities are continuous. See here. Normal component of B is continuous. I repeat, normal component of B is continuous. We know that B is equal to mu H. So I can write it as mu1 H n1 is equal to mu2 H n2. Therefore, H n1 by H n2 is equal to mu2 by mu1. So what happens to the normal component of magnetic field? So the normal component of H is discontinuous. Why? Because mu1 and mu2 varies. Okay. So it is quite opposite to the tangential components, isn't it? So there BT was discontinuous, okay, whereas HT was continuous. Note, okay, the tangential components of magnetic field was continuous, density was discontinuous, and here in this case Bn is continuous, whereas Bt is sorry, HT, right? Whereas HT HN HN, right? Normal components is discontinuous. These are the boundary conditions. Bt and HT are, Bt is discontinuous, HT is continuous, Bn is continuous, but Hn is discontinuous. This is normal components and this is tangential components. Why? Because mu1 is not equal to mu2. Therefore, Hn is discontinuous. Any doubt?
No, sir.
Yeah, please let me know if you have any doubts. At least I could see some messages on chat box, at least if you have any doubts or no.
So,
Yes,
sir, if delta H travels in two medium, so we
I'm
have to
not,
take six.
your voice is not so clear. Yes, tell
If
me.
del if delta H travels in two medium, for tangential we have to take six cases, no, sir?
Can you just repeat the question or just type the question on the chat window? Because your voice is very low. If delta H is traveling in two medium, there should be six cases in tangential mode. See, if you are asking this question here, I'll say this was a boundary which separated, I repeat, mu1 and mu2 are two different mediums. So now I'm trying to obtain the tangential components on the surface like this. This is one and this is another tangential surface. These are the only two cases. This is HT1 and this is HT2. And normal I'll be trying to get it in this way. This is BN1 and BN2. So there are two cases where I've assumed one, if I'm trying to travel, okay, if I'm traveling here from one medium and passing across the another medium through a boundary, what happens here at this point? So here at this point, you'll get two components. One is tangential component. Sorry, here I'll get normal component if I'm trying to enter from one boundary to another boundary. So similarly, if I'm trying to go on the boundary, so this is another direction, and this gives me a tangential component, and this gives normal component. So there is no six different components. So I have only two components here. One with respect to the medium one, what happens here if I'm trying to travel, whether your HT component is continuous, whether your magnetic field remains to be continuous, or it is discontinuous. Similarly, if I am trying to travel here in this direction, so this is HT2. So HT is continuous. Tangential components of H is continuous. Hope it is clear. Is it clear now? Okay. So remember these points. You could take a screenshot otherwise. So HT is continuous, BT is discontinuous. HN is discontinuous, BN is continuous. Okay, let me clear this screen now. Now the next concept which you are going to study is magnetic circuits. A very simple concept which might be a repetition of your 10 plus 2 sessions. Magnetic circuits. So what do you mean by a magnetic circuit? Magnetic circuit is a path traced by magnetic flux. So magnetic circuit is a path which can be traced back by magnetic flux. Okay. Now I just would like to introduce some fundamental jargons like keywords of magnetic circuits. So what is magnetic flux? Magnetic flux is denoted by phi. So what is magnetic flux? Can anybody answer this question? Magnetic flux is an imaginary lines of force. See here the flux lines exist. So this dotted line, say if I have a permanent magnet, north and south. So the flux lines to be like this. So it is a what? It starts from a north pole and it ends at south pole. So it is an imaginary group of lines. So it's an imaginary magnetic lines of force produced by a magnet, obviously, and it is represented by phi. What is the unit? Unit is Weber. This is one magnetic flux. Now I'll take the second concept. What do you mean by magnetomotive force? Magnetomotive, MMF. So I'll represent it here as Vm. So it is defined as a driving force. So what is magnetomotive force? Driving force which produces magnetic flux in the magnetic circuit. So it is a driving force which produces magnetic flux. So this produces what? Magnetic flux. To explain this concept, let us just imagine a conductor of this shape, a metal conductor of this shape, and you have a current carrying conductor or a coil here. This is I. So if you have a current carrying conductor like this, so there this conductor will produce us a magnetic flux, either a push or a pull force. Correct? Now if I try to bring another metal piece here, so this experiences a push or pull depending upon the direction of current. And this force which you're talking about was called as magnetic motive force. This push or pull, the force which is pushing or pulling this iron material due to the magnetic flux which was generated here, driving force due to a magnetic flux generated here due to a current, obviously, called as magnetomotive force. Remember these terminologies. Okay. I'll go to the third component. So we studied flux, we studied magnetomotive force, we studied flux, we studied magnetomotive force. Now we shall study reluctance. I'll write it as R. So what is this R? R is known as reluctance. And going back to this magnetomotive force, units ampere turns. Here it is Weber. For flux, for magnetomotive force, it is ampere turns, depending upon the number of turns of a current coil. Reluctance. So reluctance is almost similar to the resistance in electric circuit. So reluctance here, resistance R, used to oppose the flow of current, correct? Oppose the flow of current. So here reluctance, it opposes the magnetic flux. Reluctance is a measure or a property of magnetic circuit which opposes the magnetic flux. R was denoted as, or the unit of R was ohms. here the unit is mho or ampere turns per Weber. So what is reluctance? Reluctance is the property to measure the opposition of magnetic flux in any given magnetic circuit. And the unit is ampere turns per Weber or mho. Remember, it is somewhat similar to resistance in your electric circuit. And the last value, permeance. P. What do you mean by permeance? Permeance is the property of magnetic circuit which allows the magnetic flux. Okay, this is exactly opposite to your reluctance, which admits the magnetic flux, which allows, which admits magnetic flux. You can say conductor. You can say conductor in electric circuit, opposite to resistance. So what is permeance? Which allows or admits magnetic flux. Reluctance, which opposes magnetic flux. And obviously, the unit will be opposite of this, inverse, Weber per ampere turns. This can be asked as a definitions. You just need to define what do you mean by flux, magnetomotive force, reluctance, and permeance along with its units. Okay. So in this class, we have derived the equation for magnetic boundary conditions, where we saw the tangential components were continuous and Bt were discontinuous. This was continuous, whereas normal component were discontinuous, whereas B was continuous. To find this, we applied AC. To find this, we applied Gauss law. In both the cases, delta H tends to 0. This was one important derivation what we have done. And next, we have understood some keywords in magnetic circuits like flux, magnetomotive force, reluctance, and permeance along with its units. Okay, so this is all about today's class. So in tomorrow's class, we'll be discussing about two derivations. One is obtaining the expression for reluctance. So we will find the equation for reluctance R, and also we'll obtain the expression for reluctance for series magnetic circuit. Series magnetic circuit. We'll find what is the equation for R, and we'll apply this R to a series magnetic circuit, and we'll understand what happens to this R. These are the two things which has been left out in this module, and we shall go to the fifth module in the coming sessions after completing this. Is that okay?
Yes, sir.
Okay. So whatever been discussed, you kindly study only those topics from the notes which has been given, shared on the WhatsApp group. Okay. So there are plenty of other things after this uh, content, like standing wave ratio and other stuffs, reflection point. So all those things we may ignore for time being. You can make sure like you'll get um, one good question, fairly a good question with whatever syllabus that has been covered in module 4. Okay, so till the completion of this syllabus, make sure you are uh, mentally prepared to take my class uh, any moment I disclose, or any moment I just say join EMW class on WhatsApp group during this official hours. Okay, so anything from your side, just let me know.
Sir, attendance, sir.